Hello everyone, how's everybody doing? I hope you're doing fine, just like I am. I'm recovering a little bit from a bout of coronavirus, which I had this week. Fortunately, it's on its way out, it's in remission. My niece today came over, and she's daughter of a Japanese, so she has slanted eyes. And so she says that here in Germany, people are swamping the supermarkets, trying to get their food before the government quarantines the city or something. So or a lot of people are in panic mode. And I told her she's got an advantage. They all go to these aisles at the supermarket. When she goes to the aisle, all she's got to do is start coughing and sneezing. I'm sure that'll clear the aisle for her. Anyways, we got if the coronavirus doesn't kill us, we got a conference going on in Lusaka, Zambia, at the beginning of April, 4th of April. And so you better get your bags ready if you plan to go, okay? Make plans. You're going to meet some great people over there, okay? And want to make sure that people understand that we also uploaded a book, and you can download it. It's a free book. It gives you a good view of the rope hypothesis, how it explains specifically all Mother Nature's invisible stuff. It explains light, the mechanism of light, the mediator of light, gravity, magnetism, electricity, and the workings of the atom. Specifically, those five, which are the invisible stuff that Mother Nature does. And we invite anyone who wants to translate it, that book, to any other language that he might know, okay? And they need to contact us at tokakaka@hotmail.com, okay? So if you know another language, you want to translate the book into your language, we'd really appreciate it. I'm translating into Spanish. Been doing that for a little while now, on and off, whenever I get a chance, okay? Okay, today I was supposed to talk about Euclid and Aristotle and a couple of the Greeks and infinite planes. And for the third, fourth, or fifth time, I lost count, I got to postpone it one more time. We have something new come up, people who had questions, and I have to address those questions. I can't let them go by because a lot of people have doubts out there, and they say, well, what about this, And so, yeah, I want to address those issues. And I think I'm dressed appropriately today. I'm dressed in black because I'm going to go to the funeral of quantum mechanics. And that's why I thought it as a sign of respect, okay, that maybe I should dress appropriately for the occasion, okay? So yeah, we're going to celebrate, not celebrate, I mean, well, you can celebrate if you want, if that's what you want, but today is funeral day, death day for quantum mechanics, at least at this channel, okay? So I want to make sure we bury quantum mechanics, never resuscitate again. Anyone dealing with particles, or waves for that matter, which is the same thing, but anyone dealing with particles with one-way mechanisms, they die today, okay? Anyways, one of the issues that came up is this word object. And if I made a contribution to science was the definition of the word object. No one ever realized how important the word object is for the purposes of physics, that you do need to have an object to do physics, for otherwise you're introducing spirits. You're doing physics with black magic if you don't put mediators, okay? And people say, well, I can't see light, I can't see gravity, I can't see the mediator of magnetism. And yeah, you can't see it and you can't touch it because that's not the definition of the word object. And so first we need to justify that, yes, in physics, we absolutely need an object to do physics. And then if we need an object, well, then the first task of a physicist, of a true, genuine scientist, right, is to define the word object so that you can use it consistently, rationally, scientifically in a dissertation, in a debate or whatever. Okay, an exchange of ideas. Okay, so let's start. Here we have the universe without matter. Okay, looks great. Love it. Nothing there. All matter is removed from the universe. God waved his magic wand. All matter disappeared. There's nothing. There's not a single atom in that universe. What's happening there? Do you see any motion? Do you see any interaction? Okay. There's nothing there. Now you see why you need an object, because without an object, there's nothing going on to begin with. Now, what a lot of the mathematical world does is they introduced concepts. You know, they introduce field and mass and charge and force and energy and time, wave, and these do not qualify as objects. It's just that simple. They're not. You can't say you transferred energy. That's an irrational statement. You can't say you moved a mass, or that a field is vibrating. You can't say those. You can't say those. You can't make those statements in physics. They're irrational statements. You do not vibrate love. You do not move intelligence. Okay, and so yeah, people, especially in the mathematical world, they want to get away with that. Those are the explanations they give you. Those are the physical interpretation. Immediately you ask for a mechanism, for a physical interpretation, and they say, well, look, the force comes here and the energy goes there, and then here we vibrate the field, and over there we push the mass. No. Not in science. That's in ordinary speech, in religion, maybe at your church, Sunday school, fine. Take it to your priest, to your pastor, to your mullah, right? That doesn't belong in science. We do not move concept. We do not use those words, those four-letter words, as I call them, in physics. Okay? So that's the starting point. We get rid of all concepts. Now, here you have, well, let me show you something here. Okay? Here you have two magnets. Okay? The black ones there, those round circles, those are magnets. Okay? Okay, so now you see what's happening here. Put them apart, you bring them together, and they stick. Okay? So now you can say that there's an object pushing from the outside. That's a valid assumption. You can start at that point. That's fine. I say something different. I say there's something between these two that's bringing them together. Okay? But whether you push them from the outside or you bring them together from the inside, there better be some physical object in there, either in between or on the outside. But there's got to be a physical object intervening. And a lot of people say, well, but I can't see and I can't touch whatever's there. I put my hands around the magnet or between the magnets. I can't touch anything. For sure I can't see it. Yeah, because that's not the definition of the word object. That's why. See, you're using the definition of ordinary speech, which is what the mathematicians have been using for the last 2,000 years or more. So they say an object is that which you can touch. An object is that which you can see. If you can't touch or see it, it's not an object. And that's where the error is. No, an object's not that which you can touch or see. An object is that which has shape. You can have shape and not be able to touch. I mean, I can't see the air. Fortunately, Mother Nature, Father Universe, God, and the devil, all four of them got together at the bar, and they decided that they're going to make air invisible. Because imagine if they would have made air visible, that's the only thing we would see. And so, because we cannot see the air, yeah, we can touch the air, right? And we can smell it. If there's odor, you can smell it. You don't see it, but you smell it. You feel the breeze in your face. You can touch it. Okay, you don't see it, but you can touch it. But you cannot see it. And if you cannot see it, does that mean it's not an object? It's not a thing? It's not a medium? Just because you cannot see it? And yeah, in the case of magnetism, in the case of gravity, you cannot see or touch it. And so people say, oh, there's nothing there. Well, no, that's not the definition of an object. You cannot use see, touch, and you're not going to determine the presence of whatever's there with an experiment. So experimentation has nothing to do with discovering Mother Nature's, Father Universe, gods, whatever you believe in. You can't get to that through an experiment. You're not going to resolve with your senses. The only way you're going to resolve it is by pulling back and visualizing, imagining how Mother Nature is doing this magic trick. Okay? Now, is there something there? Yeah, of course. Here, between two magnets, here I've got a little, you can see this magnet is underwater, and it's drawing one iron filing at a time. Is that magic? Is that a spirit that's moving all that? Are we doing that with concepts? Are we using the word force? Are we using the word mass? Are we using the word energy to do this? Is that what's pushing it? A bunch of energy? No. There's a physical object that we can't see or touch, but the iron filing obviously can touch it. We can't, but the iron filing does, somehow. So we gotta figure out how Mother Nature does this magic trick of pulling one iron filing at a time. Okay, so you cannot say there's nothing there. Magnetic field is not nothing. It's something. As Mr. Faraday and Jimmy Maxwell, they said, there's matter in motion, some kind of exotic matter, but there's something in there that I can't see or touch. But there's something there. And if you say there's nothing, then you're a spiritualist and you're in the wrong field. You're in the wrong discipline. You should go and do religion. You're doing it with spirits. You're doing it with black magic. That's why. That's where the problem is. You're in the wrong field. Okay? So no, there is something there. We just have to identify what that something is. And before we identify what that something is, we have to know what the word something means. What do we mean when we say something? What is something? What is an object? What is a thing? That's what we need to figure out. And no one's figured that out in 2,500 years since the Greeks. Okay? So we start with the golden principle here. Okay? And the golden principle says, that's what I call it. So if you wonder what, golden principle of physics. Physics requires an object. You can't do physics without an object. Sorry. If you're going to do it without an object, you're going to say that nothing blew your house away. There was nothing there. You didn't see anything, but your house just vanished, just was wiped away. Well, then you've introduced spirits. You're introducing the god of the wind, Aeolus. You're saying the god did it. That's what you're saying. No, hopefully some physical object that you can't see blew your house away. We usually call it air or wind or some tornado. So physics requires an object. What is an object? That which has shape. Is there any provision for experiments, for observation, for touching, for seeing in that definition? Hopefully not. No, shape is a static concept. That means if there's a single object, if God only made one object in the universe, a cube, okay, that's all he made. He didn't make anything else aside from him, but he vanished too. He just made the box and then just went, to Never Land. All you have is one object. And so you got to look at it from that point of view. You got to start at that point. What is that? Is that moving? Is that made of parts? Is that, does that weigh anything? Does it have color? No, all we have is one box. That's all we have in front of us. And there you have an object. And so now you have to make the definition with that stuff. That's all you got. Now you got to get a definition for that box. Well, how are you going to define an object under those circumstances? And yeah, I always say that scientific definition of the word object destroys all religion, primarily all of mathematical physics. Physics. Big word there, okay? Yeah, so you need to define the word object. And here's the universe, and we have a single box, okay? Now you can see there's no motion. You say, well, it's got color. Well, that's only because color is you can say a wavelength. We call it a link length, but that's the same thing, no problem. It's sending color to you. But if you're not here, the box doesn't know it's got color. All it has is a certain frequency wavelength, okay? And it doesn't see itself. So it doesn't have color. It doesn't even have color to compare itself against. And the only reason you see colors there is a contrast with the black stuff, whatever that black stuff is around it. Okay, does that thing move? Well, we can set it in motion. Okay, here it is. So now it's moving. Okay, so now you can say, it's moving. But why is it moving? Because you're comparing the box against the frame, the black frame, or that within which it's moving, within your field of view. Otherwise, you would still see this. This is all you would see. Okay, so the only reason you see it moving only because you compare it against the frame. If you don't have the frame, if you have a box in outer space and that's all there is, and you're the only other guy, you have your eyes and your mind, whatever, well, then you won't see it moving because you have nothing to gauge its motion against. That's the issue. Okay, so anyone who wants to challenge the rope model should start there. Right now we have people who want to challenge the rope model, but they don't know the basics. They don't have the foundations to do physics. Specifically, they don't know what an object is. And it takes 2 years for a mathematician to learn what an object is. It really does, believe me. I mean, I had discussions with people like a fellow named Dr. Dave for months. And he just couldn't come up to the definition because it destroyed his religion, obviously. And so he argued for a long time. Another guy from Portugal, a guy went by the moniker Fiesta. These guys, they argued for a long time, for many months. And they couldn't get around the word object. And that's where we parted company because they weren't willing to accept the definition of shape. Why? Because it destroys their religion. That's why. The definition of the word object, the scientific definition of the word object, destroys your religion. You got to choose whether your God has shape or doesn't have shape. If God doesn't have shape, God's a concept, and that's what you're praying to, a concept. And if God has shape, well, that's not enough. For him to exist, he needs also location. There's got to be a straight line of direction from God to me, okay? So, and one of the things you cannot use to define the word object, okay, is synonyms. You cannot use any synonym. And here you have a list of some synonyms. None of these words can be used within the definition. And the other thing you cannot use is verbs. You cannot use motion because, as you just saw, before you can have, here, let me put it back again. There's no motion. And you already have an object. Okay, there is no motion. That means the object, the box in this case, precedes the definition of motion. You need nouns to do verbs. You cannot begin by defining verbs before you define nouns. It's the other way around. The first word a physicist must define is the word object. Then you can do whatever you want with it. But first you got to tell us what an object is. And this came about because you have a comment here by a fellow. Okay? He says the following, if I can get it. Got so many of these today. So get ready. And he says the following: a picture of a tribar is a picture. It is not an object. Oh, okay. The paper the picture is drawn on is an object. See, so we go around in circles because he hasn't defined what an object is. So he keeps going, he skips the definition, and he says, see, the paper is an object. Well, you still haven't told me what an object is, so I don't know if a paper is an object or a tribar is an object. I don't know if Superman is an object. What is an object? What do you mean when you say the word object? And then he hinted, he insinuated that he's going to accept shape. Okay, let's go with shape, but giving it little importance. So he says the definition of shape is incomplete, but let's continue. No, absolutely not. If the definition of shape is incomplete, because the definition is complete as far as we're concerned. Let me put it up there. Where is it? Go over here. Here's the definition, okay? Let me put it over here. Okay, the definition, scientific, is that which has shape. And if he says the definition of shape is incomplete, then within that definition, he's got to put whatever predicate he wants to put to condition it, to make it conditional or to change it. So he's got to say that which has shape and is black. I don't know, whatever he wants to put in there. I don't care. But he can't just say, yeah, it's that which has shape, but it's incomplete, and I'll catch you later on that. No way. No, absolutely way. Okay? So, no, if he doesn't like the definition of the word as that which has shape, he's got to qualify it within the definition. We need a definition. And then he also says, Bill's definition is not accepted by the mainstream. Well, we don't give a damn what the mainstream. You mean the mathematicians? Is that who you're saying is mainstream? These retards who come out of Cambridge and Harvard? Those are the ones we're going to respect? No, no way. They have defined the word object in 2,000 years, 2,500 at least, 3,000 maybe, right? And after so many centuries, at least many decades, they come up and they end up with ridiculous physical interpretations for phenomena. And so, no, we can't accept these people, their physical interpretations. And that's what science is about. We're saying that science is about the physical interpretations in the case of physics, right? As applied to physics. You need to explain how Mother Nature runs her shop. That's the purpose. That's what Aristotle defined physics as. You know, the study of nature. We need to figure out how Mother Nature does her stuff out there. And if these people say, well, we don't care about all that, we're going to do math, we're going to describe, and then we're going to give you a nonsensical explanation for how she does her stuff, you know, like a particle going to be at two places at once, or we're going to warp time, then we got a big problem with that, because if that's what these bozos came up with after hundreds of years of doing math, then they went on a tangent. They're not even within science anymore, okay? So I don't care what they measured. I don't care if they do experiments. I don't care if they observed. I don't care if they touched, they see, if they made predictions. I don't care about any of that. I want an explanation for how Mother Nature does gravity. And if they cannot explain it because they can't see or touch it, then that means they don't understand the scientific method. They are not doing science. They can't tell me that the Earth doesn't fly from the solar system because time is warped. And they can't tell me a particle can be at two places at once. That's not science. That's known as religion. And if quantum came up with that definition or that notion or that explanation, and relativity came up with the other, then they're part of religion. They're not part of science. Okay, I hope that's clear. Another fellow says the following. Also, he gave it his best shot. Okay, I don't mind people trying. Says that which is projected as an opposing face. In other words, again, he's introducing a second object into the picture. He's saying something is facing you, and that's what we're going to call an object. Well, that means you need two objects to do facing. When you have a single cube in the middle of space made of a single piece, let's say God just made it with his magic wand, you have an object, but you don't have any facing or anything like that. And he talked about a barrier. Well, again, you need another object to have barriers. Facing, barriers, and against, all those words imply another object. And then he uses, he proposed or introduced the words instrument and medium. Those are synonyms. We can't use synonyms to define the word object. And then he also, obviously, ended up with tangibility, because that's what opposing, what barrier, what hindrance, impediment really mean, ultimately. It means that you're bringing tangibility into the equation. That's what it means. And tangible means, touch. There it is, palpable. Means that you're going to do a verb. The moon is not an object until the asteroid hits it, touches it, comes in contact with it, is palpable to the moon. No, we can't use these definitions in science. Sorry. Those are definitions of religion, of ordinary speech, of mathematical physics. Okay, so I'm not going to answer questions to people who do not define the word object first. That's the first step. If they can't define the word object, they haven't gone through kindergarten physics. Okay, so if they want me to answer questions regarding the rope model, that's where they have to start. They have to know what an object is, because we're saying the rope is a physical object. And they say, what do you mean? You made an assumption. That's a supposition. Yeah, sorry. That's required of the scientific method, one. And second, we need an object to do physics. So I have no other choice but to do that. And so if you don't understand that, you haven't gone through kindergarten physics. Now you can say, well, we don't need an object in physics. Okay, you can fight that battle if you want. You're going to lose, but but yeah, go ahead. What the hell? Okay, now the other day I put this up. This is from the book. And what I showed there is that if you look at yourself at the bottom of a pool, like through 3 meters of water, you can see your reflection in that mirror. On the other hand, you can't see your face through a single sheet of paper, okay? And so here, let me show you the piece of paper I used there, okay? You know, you can't see your face through this thin sheet of paper. Can you see me there? No, you can't. Light doesn't go through the piece of paper, okay? So, but you know, and how many atoms are there in that thickness? How thick is that thing? Well, it's very thin. You know, it's less than a millimeter. And you have 3 meters of water, you can see yourself at the bottom of the pool. So we ran an experiment with my son, just to put here. And here you can see the sheet of paper we put in there, and you can't see through it. On the other hand, the camera is focusing on the mirror, okay? There we film ourselves through the mirror, okay? And we can see ourselves through there, but we can't see ourselves through the thin sheet of paper that we put in between. Okay, I hope that's clear. You can't see the mirror doesn't go through there, your face doesn't go through there, okay? On the other hand, when we put it under water, and here I took 2 feet of water that I put in there with a mirror at the bottom of my trash can, my kitchen trash can, we filled it up with water. And after filling it up, okay, give me a second here, there you go. Filled it with water, and yeah, we can see our image at the bottom of the trash can. There it is. See, we can see ourselves right through the water. Okay, we can film ourselves there. So yeah, the point of that was to show that, yeah, you can see yourself through water in a mirror that's at the bottom of your trash can, or your pool, whatever, right? And so one of the comments that came back is that, oh, see, you do need experiments. You do experiments in science, see, because you did an experiment. My God, it's like, you know, you point to the moon and they're staring at your finger. You say, no, I want you to look at the moon. No, but I saw your finger. That's how these people are, you know, I'm sorry. And these are a couple of comments that were made regarding observation. And one of the things we want to destroy here is the word observation and observer. There are no observers, there are no observations in science. Okay, that's mathematical physics. Okay, scientific method is you have to have a way of explaining something in a rational manner to another human being. Yeah, true. Something like what? Yeah, something like an observation. Which is not a part of science. He asked that question rhetorically. Observation is the only way, is the only reason why any hypothesis is rooted in reality. Otherwise, your hypothesis is a dream. That's one comment. Another guy said, how can you give a rational explanation to anything physics if you refuse to make observation? Blah, 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 and experiments, okay? Yeah, in science, we don't do observations, we don't do experiments. And one guy said, well, but you just did an experiment. Yeah, but the experiment is not science. It's not part of science, it's not even part of physics. Okay? And you say, why? How can you explain something if you have not observed it? And people miss the point. Science is not gawking. You know, I can make an experiment all day long. And I always do my famous drop the pen experiment. Okay, so here it goes. Okay, watch closely. Always fall to the floor. And I do it 100 times. And I observe it 100 times, and I measure. And I make my calculation, get the equation, you know, get everything right, and make sure I get the measurements very precisely. So I did science. Is that science? Just dropping a pen 100 times and saying, oh yeah, I did science. I observed. I did an experiment 100 times, repeatable. No, science is telling, I don't care what you did in your dark basement. You can do whatever experiment you want in your dark basement. When you come to the conference, to the scientific conference, to the physics conference, we need an explanation, not for you to describe and just tell us a little fairy tale that, oh yeah, I did experiments. I observed. I measured, I calculated, I made a prediction that the pen would fall again. Who cares about all that stuff? I want to know how the magician did the trick. That's what science is. That's where you have to use your brain. Measuring, you don't have to use your brain. You just take the ruler, measure, make a predetermined standard and say, well, this is the meter. And how much did your table measure? Well, it measured 1 meter. And I measured it 100 times, plus or minus, error factor. That's not science. So observing, doing experiments, and calculating, those do not qualify as science. Science is explanation, not observation, not experimentation, not calculation, not prediction, none of those. Science is explanation because that's where you have to use your cocoa. That's why. Okay, and so the fact that I did an experiment, it's not because I was doing science. I was trying to make sure that people understood that when you look at the bottom of a pool, 10-meter pool, or 3-meter or whatever, 10 feet pool, depth, deep, you can see your face in the mirror down there. And I did a very quick back of the napkin type experiment, 2 feet of water. Yeah, you can see your reflection at the bottom of that, through the water. And so the question is, how light went round trip? Because otherwise people will say, oh, light came one way, came from the bottom of the pool to you. Like when you look at the drain in a pool, you can see it through the water, but people say, okay, the light came to me one way. No, this is a round trip. You put a mirror down there, you can see your face. That means light had to go through all that water, 3 feet or whatever of water, the 3 meters, and then come through the water and back to your eyes. Okay, so it's round trip. That's the point. Is that science? No, science is the, now you got to explain how that happened. How Mother Nature did that magic trick. That's where science comes in. But people say, oh, you got to observe. Well, did Stephen Hawking ever observe a black hole? Obviously, he did not. He doesn't even know what a black hole looked like ever in his life. Okay, so no, you don't have to observe. You have to explain. And he explained it with mass, black hole. That's a long story. Anyways, so one fellow came up there and he says, that I used the wrong, that I misrepresented quantum mechanics. That what I did, he says, Bill's version of why light slows down is antiquated, a point I've made before. Here is a video because we avoid equations on this channel. Yeah, we avoid equations that have nothing to do with science. We need to have an explanation, not equations, okay? So don't take it bad. It's just a question of definitions. Otherwise, your job is to define. This video provides the latest theory. Again, I'm not saying this is right. I'm saying that Bill's 2 explanations, which this person talks about, were not the accepted mechanisms. So what did I say to that? Well, here's the transcript of what I said exactly, and I essentially mentioned 2 mechanisms. In one, I said, let's go with number 2 first. One is the pinball machine. The photon just goes and hits all these atoms that form the glass through which it's supposedly going to go through. Some is going to reflect, some is going to refract, but it's going to go and hit all these little atoms and then go through. And that's the pinball machine notion of quantum mechanics. Well, that's been rejected by people in quantum mechanics because they figured out that that couldn't be for whatever reasons. So let's go with number 1, which is the one that still is in vogue, and that is that the atom does absorb the photon. That is what quantum mechanics says. Now, what I did not clarify last week, because I didn't go into any detail in this, is that, yeah, even though the atom absorbs it, right? Let me get back in here. Give me a second. I got so many of these that, there we go. The atom absorbs light and then re-emits it. But what happens? The way the mathematicians explain this is that when the photon comes in, it hits the atom. In other words, it hits the electron, essentially. And the electron, of course, is both, because they have to make this magical assumption, is both a particle and a wave. They say it behaves, but it's the same thing to say behave and that it is. but they never understood that. So what happens is the photon excites the electron. The electron now waves. And now we have waves of electrons and waves of photons. We have waves of light and waves of the atoms or the electrons, the valence maybe, shell, that's not clear, but they wave. And so we have these two waves inside the glass, and that slows the wave of light down. Okay, that's their argument. Okay, and so I tried to illustrate that, and well, this is the what he pointed. This was the website he pointed to, and as you can see, the light is traveling into the glass, and then it changes abruptly. Why? Because he says that's where we have a combination of two fields or two waves or whatever. Okay, and that wave or that field or whatever magical substance they introduce in there, that slows light down because the two waves combine, and that slows the incoming light wave. Okay, that's their argument essentially. Okay, but it's the same because the point was that the atom absorbs a photon of light. That's part of quantum mechanics. You can't change that. But then what they had to do, they said, well, what it does is it excites the electron, and that creates waves, and those waves slow down the wave of light. That's their argument. Okay. Now, what is the problem with that? Well, the problem is that that contradicts the wave equation. Okay. That's the problem. The problem is you have the wave equation, and the wave equation is that the velocity of light, little c, is equal to lambda times frequency. In other words, lambda being the wavelength. So you have frequency times wavelength, and that gives you the velocity of light. What these people are saying is what I showed in the little picture that I had as an advertisement for this video, where the car crashes against a tree or whatever, and what continues is part of the wave and part of it stays behind. In other words, the wave flattens or shortens, right? Because it hit a brick wall. And so the wave becomes shorter. But the frequency remains the same. And so if you multiply frequency times wavelength, you get a velocity which is lower than light. Okay, so what they do is play around with a wavelength and leave frequency alone. Okay, I'll illustrate that in a second here. Okay, and here's the illustration that I put. Okay, got so many of these it's going to take a little time. And well, this is another one. Anyways, you can see the waves coming into glass. Okay, and they hit a brick wall, and within the glass they travel slower because why? What has shrunk is the wavelength. The frequency remains the same, but the wavelength has shortened. And you can see that the frequency remains the same because I put those little markers there, those lines, and you can see that every wave that passes through there is the same, whether it's in the air on the outside of the glass or within the glass. It doesn't matter. The number of waves that go through that point, which is the frequency, remains the same. The only thing that changes is the fact that the wave is flattened out. In other words, in the direction of motion. In other words, the wavelength has shrunk, is shorter. Okay? And so here is the picture that I had. You know, you hit a brick wall and the car stops, but the wave continues. And what's continuing? The frequency. That's what continues. But the car, which is in this case the wavelength, has now shrunk or stopped or become shorter or whatever. Okay, so this is what they're saying. They're saying the wave shrunk, okay, in the direction of motion because it hit a brick wall. But the frequency remains the same. And that's why the velocity of light is lower. In the case of glass, if we're going to use 1.5 as the refractive index, that means that if light travels at 300,000 kilometers per second through the vacuum, more or less through the air, when it hits glass, it's going to travel 200,000 kilometers per second. What does that mean? It means that frequency remains the same. That means C equals frequency, same frequency, whatever. You can use that as a constant. But what changes the wavelength? It's shortened now. It's smaller. It's shorter. And so you have a slower speed of light through glass. That's the notion that they have, okay? what is the problem with this? Well, let me show you a couple of, you probably heard of the Stack Exchange. It's run by a guy named John Rennie. He's a very important guy within the world of censorship. That's what they do. They censor anyone who doesn't believe like they do, and they control these magazines, these outlets, where they feed the public whatever they want, but they won't allow you to feed the same thing through their sites. And the Stack Exchange, they had several people. Someone asked this question about light, and these are the answers he got. Okay, and that's where you're going to see that these guys have no clue whatsoever. Okay, these were the answers from official site here. Okay, that's what we're talking about. Okay, here's the first one. Okay, it says, what determines color, wavelength, or frequency? And one guy answered, wavelength, the length of a signal defined by the speed of light, 300,000 kilometers, you put per hour, per second, divided by frequency. For almost all detectors, it is actually the energy of the photon that is the attribute that is detected, and the energy is not changed by a refractive medium. So the color is unchanged by the medium. Color is defined by the eye, okay, and only indirectly from physical properties like wavelength and frequency. So this guy says it's what you see, and not that something has changed the color has changed inside the medium, okay? What's another guy say? Okay, because we had all kinds of opinions here. I like it because, there's no unanimous idea on this. Here's another guy, and he says, refraction experiments show it is the frequency that determines color. Blah, 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 blah. He justifies that. Okay, what does another guy say? Well, another guy says, see if I can get him up here. Another guy says, frequency of light wave does not change from medium to medium, while the speed of light, and thus wavelength, does. So again, he agrees with the previous guy, okay? And so he says the wavelength is what shrinks, but the frequency remains the same, okay? Essentially what these people are saying is that, let's see if I can get this thing up there. They're saying this. They're saying that here you have wave equation, okay? And that's C equals lambda times frequency, okay? And what they're trying to do is get rid of lambda, or they're trying to shrink it, or they're only going to play around with lambda. They're only going to play around with wavelength. They're not going to touch frequency. Why? Because if you look up frequency, it's equal to the Planck's constant times energy, okay? And if you replace that in the first equation, then you get little c equals lambda times energy over, Planck's constant, okay? So what happens? Energy is equal to now velocity of light times Planck's constant over lambda. So no matter how you turn and twist it, you're not going to get rid of lambda, okay? And so you see in the Wikipedia, very interesting line there. It says, as h and c, Planck's constant and velocity of light, are both constants, photon energy, E, right, changes in inverse relation to what? To wavelength. Energy is wavelength dependent. That's what it's got to be, because you can't get rid of lambda. That's why. Lambda has to be in there. And so no matter how you turn the thing around, you can say lambda is equal to hc over E, frequency is equal to c over lambda, and eventually you come back to where you started. C equals frequency times lambda. And lambda is related to so-called energy mathematically. So you can't get rid of lambda no matter what you do. And what these people want to do is, they say the wave equation, essentially, that's been around at least since the 18th century, the Lambert and Euler, these guys came up with the wave equation, which was later modified over the years and applied to light after Maxwell did his magical math, okay? And yeah, today we have that equation. We know that little c, velocity of light in a vacuum, right, is equal to lambda wavelength times frequency. And what these people want to do is say, well, frequency is dependent on energy, or energy is dependent on frequency. But they want to give you the idea that energy is not dependent on lambda, on wavelength. And that's not true, because the equation says so. So you can't get rid of lambda and just play around with one part of the equation, which is what they're doing. And so because of that, you have a fight within the stack exchange. Here are the other opinions of the experts. Okay, here you have the other experts, and they say something different. Say, actually, there is something important all these answers are missing. Color is determined by the response of the human eye, not by energy or frequency. That's one guy, okay? And let me get to the next one. Another fellow says, where is it? There it is. They're just so far down to bring them up. Okay, what does one guy say? Well, several guys. These are 4 different guys. What determines color, wavelength, or frequency? I think it is wavelength. And the other guy said, in my opinion, both. And the other guy said, light, frequency, and wavelength are inversely proportional, which is correct. They're inversely proportional. You can't get rid of wavelength and just say, I'm just going to play with a wavelength, lower it and raise it, whatever. They want to get rid. They want to only play with a wavelength because they say energy is frequency dependent, but it turns out energy is also wavelength dependent. So we're going to say we haven't eliminated lambda from there. And then the other guy says, which is correct, since both C and N are constant, there is a fixed frequency for any given wavelength. That's a true statement. You cannot, from a mathematical point of view, at least get rid or just play around with wavelength. And this is what these people are saying. And this is where the problem is, okay? The problem is that they just want to play around with a frequency. And here, let's see if I can find it. Here you have the spectrum, okay? This is the spectrum of light, okay? And some people sometimes put frequency in there, but most people just put the wavelength. They just show that light is a function of wavelength. And short wavelength, you get into the gamma rays, and long wavelength, you get into the infrared, etc. Okay? You can't avoid it. And under the rope model, it's very clear. A rope either has longer links and fewer links, or it has shorter links and many links. That's all there is. So under the rope model is consistent with that, but we do not shrink you cannot shrink just the link length and say the frequency remains the same, okay? Which is what these people are essentially saying. And here, you can see it here in my good old rope, okay? Very simple, okay? Okay, how many links do I have there? Oh, let's see, make it a little longer here. We have what? 1, 2, 3, 4 links, okay? So if I untorque it, okay? Now I only have, what, 1 or 2 links right there? And now each link is longer, okay? And I have fewer links. And if I torque it again, okay, now I have more links and each link is shorter. C equals frequency times wavelength. There you have it. It's the equation of a rope. And none of these bozos of mathematical physics ever figured that out because they never thought that there could be a mediator between 2 atoms. They think that the atom just shoots one-way bullets or arrows or whatever, okay, into nothingness. And if you catch it, well, then you get light. That doesn't work. It goes from atom to atom. Okay, you can't avoid that under the rope model. Okay, so what is the issue? Well, that was one issue. The other issue here is this fellow really believes in, guy who wrote a lot of this stuff, believes in fairy tales. You heard of you heard of Bugs Bunny, and Bugs Bunny, he watches TV. This guy watches TV. He sees Bugs Bunny there, and he says, rabbits talk. Rabbits talk? What do you mean rabbits talk? Yeah. I saw a rabbit talking yesterday on TV. His name was Bugs Bunny. Huh? And what did he say? Well, he said, here it is. He said, what's up, Doc? That's what he said. Okay, so he kept just saying, what's up, Doc, in every film that I saw. So this guy believes that bunnies talk because of this. He reaches this conclusion that bunnies must talk because he saw it on TV. This is how naive he is. And he says the following. He puts this comment, which made me laugh, really. He says the following. He says, Bill claims that when light goes through a dense medium, it changes lengths, short, long, okay? We should see a change in color. We do not. We do not see a change in color. Well, you can't see inside there, right? Please look at a reference below. It shows speed slowing down and no change in color. I said, what is this guy talking about? He probably saw Bugs Bunny. And he's saying, oh, I saw Bugs Bunny, you know. So that's how he's saying, that's how naive he is. You say, well, what did this guy see? And so this is where he sends me. And I went in there and see, well, let's see what it is he saw. This is what he saw. This is from their site, okay? And when he says, see, you got all that light going through there. You got this little blob there, and suddenly you got this light going through there, and they're filming this light, right? And he says it hits this Bose condensate blob there, and see, light doesn't change color, he says. And I'm saying, what the hell? He thinks this is real. He thinks this is Bugs Bunny talking. He thinks that this is real. This is a real film. That's what he thinks, okay? And so it just kind of made me laugh that he took this at face value, that he thought he was looking at something that is real, that was like film, like you got your camera and you see the photons passing by you and you say, oh, I'm going to film the photons. And here I'm going to show Bill that light does not change. The color remains, see, it was always remain red. And if you go in there into this paper, because if you go to the authentic paper, the original paper, you see something like this. They have this in their paper. This is a picture from their paper. And you see the finish line, and one photon reaches faster than the other one, the one who got stuck in the Bose-Einstein condensate. And so, you know, he probably thinks this is real. He probably thinks there is a finish line, one photon beat the other one. He thinks all this stuff is for real. And what you'll find out there is the following. If you go to the original paper, okay, because that's where you got to really go. You can't go to the translations for normal people, for people who are not familiar with all these things. And it says the following. I just pulled one piece which essentially puts all of this into proper perspective. It says a schematic of the experimental setup. Light and electron pulses, okay, at a variable time delay are spatially overlap on an isolated, silver nanowire suspended on TEM grid, blah, 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 blah. Probing electrons are detected using a CCD camera after passing through an electron imaging filter. What are these four-letter words? What are they talking about? What is a CCD camera? And what are they talking about imaging here? So we got to look that up, because that's where the key is. You know, that's where the mystery is going to be. And so you look up the word CCD camera, and this is what you find, okay? It says a charge-coupled device. CCD is a device for the movement of electrical charge. This is from the Wikipedia. Charge, oh, we got a problem there already. Charge is a concept, so you can't have movement of concepts. But let's continue. Usually from within the device to an area where the charge can be manipulated, such as conversion into a digital value. Okay, so what they're doing is taking the movement of something they don't know, a concept, charge, or a pulse, or a signal, right? And they're going to turn it into a digital value. They're going to turn it into a particle. That's what they're saying there. Okay, they're going to assume it's a particle. This is achieved by shifting the signals between stages within the device one at a time. In other words, they're going to go in there and they're going to say, hey, you know, energy comes in discrete packets according to Mr. Planck. So they're going to treat those as balls, as discrete balls. That's what they're doing. CCDs move charge between capacitive bins in the device with a shift allowing for the transfer of charge between bins. And then it says CCD is a major technology for digital imaging, etc., 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 okay? And so we say, well, what the hell is this digital imaging? Let's get to the bottom of that now. Okay, so you look up digital imaging to find out what these people are doing in the labs, okay, how they're figuring all this stuff out. It says digital imaging or digital image acquisition is the creation of a digitally encoded representation of the visual characteristics of an object. Okay, they're going to take a signal, they're going to take a pulse, and they're going to turn it into a ball. They're going to say, we're going to assume that what just went through our eyes is a little tiny ball. That's what they're doing. Okay? Digital imaging can be classified by the type of electromagnetic radiation or other waves. They're already assuming they're staring at a wave, and they're going to turn that wave into a wave packet, whose variable attenuation as they pass through or reflect off objects conveys the information that constitutes the image. They're gonna convert these signals into images. They're gonna take that information, that pulse, whatever it is, and they're gonna turn it into a particle. Okay? And again, information is converted by image sensors into digital signals that are processed by a computer. Okay? And essentially, what has happened is that all these, see, I worked in the industry for a long time, and there's something called a photomultiplier. Photomultiplier already assumes it's built already to consider all pulses, all signals as particles, as discrete particles, because that's what quantum tells them. So they're going to build a device already saying, look, we're going to detect this electronically. They're going to do it with electrons. They're going to try to figure out what a photon is with electrons. Is that what they're going to do? Of course you can't. You can't see an invisible entity like the mediator of light. You can't touch it. You can't see it. Much less are you going to detect it with electrons, but that's what they do. So you say, well, what are they really doing with this? What is this technology? Well, the technology is every time you see a signal, you turn it into a wave packet. What is a wave packet? A little ball. And you're going to treat it as a digital, little piece of energy, a ball of energy. And so the system is already designed to consider all these things as balls to begin with because it's designed that way. And so people say, oh, see, you proved that it's a particle. No, you didn't prove that it's a particle. You did not see the particle go by. That's all imaging. But this guy believes that, Bugs Bunny is for real. He looks at these things, so gullible that he looks at all this stuff and he thinks he's looking at the real thing. Let me show you a couple other real things that they should feed the public, okay? Just so you're aware how these people manage the information. Here you have a fellow by the name of Tanamura, a Japanese guy who works for, for Hitachi Corporation. Okay, and this guy, he says that he did the slit experiment. He said, when accumulated, interference fringes are formed, okay? And he says, we have reached a conclusion which is far from what our common sense tells us, for sure, no doubt about it. What is he saying? He's saying, if you shoot these little dots, these spots indicate individual electrons. Electrons are detected one by one as particles. You can be confident that electrons are particles. He's already concluded, he's got this foregone conclusion that what you're staring at is a bunch of bullets hitting on the wall. And that's what it looks like. You look at that and say, well, he's right. I mean, that's what it looks like. He's shooting a bunch of bullets, okay? Is there any way to doubt this? Is there any way to challenge this? Is there an alternative? Well, this is Tanamura's version of this, okay? This is what he thinks it is. He thinks he's in a target practice. He's at the shooting range, right? And he's going to create all these little fringes with bullets. That's what he's saying. He's saying you're going to get in there with your shotgun, right? You're going to shoot, okay? And then when it comes over, you can see all the holes that you made in your target, and you say, this is obviously the electron is a bullet. See, it just went through and killed the guy there. Made these patterns, okay? That's what he's saying. And again, is there an alternative to this? Well, I think there is. Let's see if I can find it here. I lost it here. Give me a second here. Still not fine. Well, I'm going to have to go with the next one until I figure it out. I wanted to show you that. Maybe I'll figure it out still. Anyways, here's another fable that these people tell you. Okay, and this is the one that won the Carl Anderson the Nobel Prize. He says, what I found is a positron trace, a little particle that went in there and made that groove on a wafer, on a piece of metal. Okay, and why is this nonsense? Well, first of all, it's a suppositron, not a positron. He supposed that it was a little particle that made that little scratch. Okay, and why is that not possible? Well, because these things travel at the speed of light. This guy's saying that it made that curve in such a short time, in such a short distance. Okay, and the question is whether that's realistic. Let me give you some more. And again, these are assumptions. He's assuming that the positron is a little ball. And so he's saying, it made that curve, made that groove, like it plowed through the field. Well, did the positron go up and down and make one little hole at a time? Is that how he built that? Or was it, did it plow across the field? These are important physical questions. They're not important for him because he's a mathematician, but for a physicist, these are the questions he would ask. Let me give you another example here. Again, of how these people make claims that people take at face value. They're looking at Bugs Bunny and they think Bugs Bunny is for real. And this is one of the famous one that came lately, I think 2013, 2014. This is a Swedish group that said they filmed an electron. And you see the electron there. You say, oh, that's what an electron looks like? Okay, now we've got it all settled. There's a couple problems with this. The first one is that an electron is supposed to be zero-dimensional. It has no size. So the question is, what did these people film? And that's only the beginning question. There's even a more profound question is, and I'll just go with the next one before I answer that question or clarify that. Here's another one. This is by a government agency in the United States known as Brookhaven National Labs. Okay, and what you see there is the explosion of two gold atoms. They collided, and from that collision you get this image. And they put that like on everywhere. Anyone who missed that is not into physics or doesn't do any research. And so you look at it and you say, hold it, gold atom has only got like 74 or so, I can't remember the exact number of particles. And they say, no, it's got more particles. See, what you're looking at there is gluons and quarks. They clashed and they broke up into a gazillion pieces. And what you see, all these gluons and quarks rushing away from ground zero. So here we've filmed the electron. We've seen the positron because it made the groove, right, in Carl Anderson's suppositron paper, for which he won the Nobel Prize. Here you have gluons and quarks. You're talking about very small subatomic particles. Just to put it in the right perspective, let's see if I can get these. I got so many right at the bottom, sometimes I can't even get them right. Here's the quark, okay? So you can see what the size of a quark is in proportion, right? Here you have a proton, and a proton is made of 3 quarks, also a neutron for that matter. And they have these bed springs they call gluons. Actually, gluon is another particle that is mediating this transaction. Of course, they cannot illustrate it with particles because particles don't pull, so they had to put a bed spring in there. But you can see if this is a proton, and a proton is a small part of the atom, like a 10,000th part of the entire volume that a hydrogen atom occupies. If a proton is 1/10,000th part, and within that you have these quarks which are smaller than the proton, which make up the proton, and within that you have all these gluons which are really particles, gazillions of particles that bring the quarks together, right? And these people say that they've already filmed the quarks, the gluons, the electrons. Then the question is, oh man, they should be able to draw an atom. I mean, if we're filming electrons, and the electron has no size, but they say they filmed it, okay, fine, let's concede that. No one should have any excuse not to draw, to sketch a hydrogen atom. And these people say, well, we can't see an atom. What do you mean? You've got all these electrons and gluons and quarks, which is a tiny, small, vanishingly small part of an atom. You've imaged them somehow. You claim that that's truth, but you can't tell me what an atom looks like, which is billions of times bigger than these guys. We got a problem because something is wrong. Something is wrong somewhere. You can't say it's. I give the example of the architect that comes to your house, or the builder, and you say, what does my house look like? He says, oh, I can't tell you. I work with nails, and I use the nails to put the boards that make the wall, but I don't know what your house looks like. I mean, if you're working at the nail level, you had better know what the house looks like. And that's the case here. Here, these people are saying, we know what an electron looks like, we know what a gluon looks like, we know what a quark looks like, but we don't know what an atom looks like. They can't draw an atom. And you say, why can't you draw an atom? I mean, you're working at the quark level, at the gluon level, at the electron level. We've never seen one. We don't have enough equipment, the atomic force microscope or the scanning electron microscope, to be able to see a hydrogen atom. We got a problem because these guys already are working at subatomic particles. So no, we got a problem. We got a serious problem because these people are making claims based on the particle hypothesis, which is already a foregone conclusion, and that's what they build into these devices like photomultipliers and these CCDs. What they do is they already built in the particle notion, and they treat everything as particle. Any blip, any pulse, any signal is treated as a particle. And so people say, oh, look, they've proven that the world is made of particles. No, it's the other way around. The devices are built based on quantum. That's how it works. And so everything will be confirmed from now on because all the devices are made to detect everything as particles. They turn everything into digital pulses. They've never seen the mediator of light. They've never seen a photon, but this guy believes that they filmed the photons. You see, the photon doesn't change its color when it goes through the Bose-Einstein condensate. He really believes he's looking at Mickey Mouse and Bugs Bunny and who knows what, and he thinks it's really Mickey Mouse there. No, these are all images. These are images that these people fabricate to give their physical interpretation. That's why the color remains the same. That's the only reason, okay? Okay, moving on here. Let's see if we can do a little closer. Today I'm going to go a little over time, I guess, because I need to cover a couple subjects here. Maybe I'll keep them for next time. Who knows? This guy says, issue with light underwater. Bill says that when light goes through water, then the electromagnetic rope change wavelength and frequency. Yeah. He explains this by saying the links get longer. Not shorter. They get longer. That's why, and again, here you have it. Frequency times wavelength. Okay, so when it goes through a denser medium, what happens is the rope in other words, the links become longer, and and frequency changes in inverse proportion. That's what it is. That's what C equals frequency times wavelength means. That's the equation of a rope. And as you can see, they try to hold frequency constant, but wavelength, they shorten and, they play around with a wavelength. And this guy doesn't understand that. He thinks that there's no change in color inside there. But he says this means that the color that we should see will change from white, average of all colors, above the water, to red or any other color with a longer wavelength. I don't know where he got that at all. He's putting words in my mouth. His interpretation is his own. I don't know where he got that. When you go to see the paper that he references, okay, see if I can find it here. I need a secretary. That's what I need. Okay. Okay. Well, he just insisted on that. He's saying he comes up with notion. He said, but we know that colored light has different penetration rates through water. This shows red penetrates only a few meters versus blue, which penetrates hundreds of meters, seen many times by underwater cameraman and scuba divers. And he references an article, which again I pulled up. If Bill is correct and the electromagnetic links get larger, then we should have a red ocean. I don't know where he got that. That's his interpretation, okay? And anyways, I went to see the article, see what he's talking about, and the article says exactly what I thought it would, no difference from what the paper said and what the rope model proposes. There's no contradiction. And here's the paper, okay? This is the picture. You can see what he's talking about. He's saying when light, like from the sun, hits an ocean, well, the high frequency rays, like blue in this case, go deeper, and the red ones, the lower frequency, the longer wavelength, don't go as deep. And that's got to do with, again, with the so-called energy content, okay? No problem with the rope model. Were you saying that long link is cold, short link, hot? Very simple, hot and cold, that's all it is. And the hot ones have obviously more energy. That's the word the mathematicians use to say something that's got short wavelength. And yeah, it's hotter. And it's got higher frequency, higher energy because of that, and it goes deeper. No problem. We have no difference with what these people figured out there. Okay, there's no contradiction. And let's see if I can see. Okay. So when light goes through a medium, like in this case, which I showed the other day, okay, with particles, which is what they use, right? They have to use Snell's law, and they say, look, what changes here is the wavelength. Okay, the wavelength is what shortens, and because of that, light travels slower. Because the only way you're going to get a proper version of why light travels slower through a medium is if you shorten the wavelength, if you keep the frequency constant. In other words, here what we're doing is saying essentially the following. If you have, let's say, just give an example, a 500 nanometer wavelength times whatever frequency, the only way you're going to get a slower speed of light is bringing that wavelength to, say, 400. And now you have 400 nanometers times the same frequency, and of course you're going to get a lower number, and that's what they do with the refractive index. But what is the physical interpretation? Well, they say the explanation is first that the atom absorbs that incoming ray of light, okay, that photon, and because of that it vibrates, and because it vibrates, okay, it forms its own waves. You can say the electron waves, okay, inside the layer. And so you have the wave of light and the wave of the electron wave, and they kind of mix with each other. And because they mix, light goes slower through the medium. That's how they explain it today, okay? But again, we have no mechanism. Why? First, they use a magic wand to convert it into a wave. There's no such thing as a wave in quantum. You don't believe me? Go to look at the standard model and see if you see anything called wave in there. That's all particles, all little balls, little beads. They have all these names, gluon and proton and whatever. They're all little beads. And so you won't see the word wave in there. You won't see a transverse wave. But they use the transverse wave when they need to explain these kinds of things, or maybe the slit experiment or whatever. That's when they introduce the wave. It's a nagging problem that Mother Nature imposes upon the mathematicians. They don't like the wave, but they have to accept it because Mother Nature says, light behaves as a wave. And they can't get rid of that. Maxwell told them that they can't get rid of that, okay? So they use the wave. And so that's the first problem. They use a wave, and there's no such thing as a wave. Because when you say, well, what's a wave? Well, it's all these particles that are waving. So we're back to the particle. And so whenever they talk about wave, they're talking about particles. But they're saying the particles called photons and the particles called electrons. They move together. And why would that slow light down? We still have no mechanism You know, they have to illustrate that for us. Say, well, why does it move like that? Why does the wave of light move slower? Because there's a wave of electrons. What is the wave doing to the wave, in other words? I mean, if they're all particles, right? And again, are these particles traveling through, or are they already there and waving one on top of the other? I mean, what's the mechanism? I need to see a film of this. And this is what we don't find. We don't find a mechanism, a physical interpretation. All they say is, oh, we have one wave and another wave, and one goes slower, the other one's faster. They both superimpose, and the guy that's coming in, he goes slower. That's what they're saying. You know, and so, yeah, that's what we have to this day. Here we have, see if I can pull it up here. See if this one's it. Now this is the quantum, and see, because it all comes down to the atom. Unless they can draw an atom, we cannot begin to talk about the wave. We cannot begin to talk about light or anything else. We need to know what an atom looks like. And specifically, we need to know what's between an electron and the proton. We need to know what's in that region in a hydrogen atom. This is what they need to identify. If they can't identify that region there, they cannot draw their atom, because their atom is just, you know, one ball, the proton, which is made of those quarks and the gluons, and you have the electron on the outside. So what keeps the electron faithful to that nucleus, to that proton? I need to identify that region between the electron and the proton. And unless we get that, we cannot even talk about waves. We cannot talk about electrons flowing as little beads, because we still don't have an atom. How do you know the electron is a little ball, a little bead, when the electron has no size, according to them? The photon has no size. We're talking about sizeless things. And what is a thing? It's that which has shape. These people say these things don't have shape. So what are we talking about? What are we moving here? Concepts? How can you talk about the flow of electrons making up electricity, for example? Or how can you talk about the electron being, or the atom being ionized when you remove an electron? What keeps it there to begin with? Please draw your atom. And I don't care if Mother Nature's real atom. I want your atom. I want you to draw your atom. What are you visualizing when you say that electricity is the flow of electrons? Or that when there's a quantum jump, when the little bead goes back and forth between energy levels, it emits and absorbs photons. What do you mean by that? I mean, what do you mean? This little ball jumps back and forth and somehow it emits, creates photons and absorbs photons, little balls? So you have a little ball that's going back and forth, a sizeless ball, right? And it's absorbing and emitting another sizeless ball called a photon. So far, we have nothing in front of us. That's what we have from physics point of view. And unless they clarify that, unless you can give me a model of your atom, and again, I don't care about Mother Nature's atom, or the real atom. I want your atom. I want you to explain in your own terms what your atom looks like. Just draw it. Very simple. I mean, if we're talking about two particles, how difficult can it be? You got a ball, proton, and you got a little ball, an electron. Fine. What keeps the electron bound to the proton? And if you cannot justify that, you got a nonsense atom. And of course, you're not going to understand anything, and you should not be able to explain light or any of these other features of quantum mechanics, of what quantum mechanics alleges. And that's where quantum mechanics fails. It fails because it has not determined what light is, because it has not determined what an electron is, because it has not determined what an atom looks like. But see, they make all these claims that they filmed the electron moving, that they can film a photon, which is what this guy proposed. He says, oh, look, it doesn't change colors when it goes through the Bose-Einstein condensate. They have already filmed and talked to and interviewed the quarks and the gluons, which are inside the nucleus, which is the 10,000th part of an atom. They've seen all these tiny ones, but they can't tell me what an atom looks like. They cannot draw an atom for me. And when they do, they can't justify how the electron remains faithful to the proton. So yeah, that's where they should start. And so, you know, what I'm going to do, anyone who wants to criticize the rope model has to start by defining what an object is. And then it'd be nice if they draw first their atom. I want an atom. I want a picture of their atom. They can point to it anywhere on the internet and say, look, here it is. Here's my atom. And I don't care about Mother Nature's atom. I want their atom. It's just you and me, bud, on this island. There's no one behind you, so don't look behind and say, oh, all these guys stand behind you. They all approved of my atom. No, no. It's just you and me. We're just alone on the island. So all you got to do is draw your atom and justify it. You got to say, look, this is how the electron remains faithful to the proton. If you can do that, hey, I'll eat my words. Anyways, I'm going to continue a little bit along these lines on Wednesday because I haven't finished here completely and I want to cover a couple more points, just too lengthy to cover all these little details. But the bottom line is I need an object and I need the atom. So anyone who wants to challenge any part of the rope model has to produce those two. And by the way, if you want like extra credit, tell me how two particles can be at the same place at the same time. Because people say, oh, but your ropes go through each other. Everybody asks that question, but nobody asks, well, how can two particles go through each other? How can two particles be at the same place at the same time? How can one particle be at two places at the same time? Nobody asks. Everybody takes that as a given because it comes from the scientists, mathematicians. So that's okay. You don't question that. But the first thing people question about the rope model is touching, seeing. And we say that, you can't see or touch the mediator of light. So yeah, that's extra credit for anyone who wants it. But first, object definition. How do you define a word? You put the word object, colon, and some words after that. That's the only way that's going to be accepted. You can't say, well, let me explain it. No. We need a definition. Object, colon, followed by words that define the word object. That's the way it works. Okay? That's the first step. The second step, hey, draw an atom for me. Any atom. You can draw the hydrogen atom is the simplest, so that's the one I suggest. And justify how the electron remains faithful to the proton. Then we can start. Okay? And that's before you can make any criticism of the rope model, because that means you have nothing to offer in the alternative, and you haven't gone through the kindergarten class of physics. We'll see you on Wednesday. Bye-bye.